It's really a pleasure having you and having an interview for our course on materials characterization at UPB. So, first question, very quickly. The discovery of C60, later baptized as by you as buckyball, is based on your work on molecular spectroscopy. How do you think that material characterization techniques should be considered for the new materials science education?
I think it's important to realize that the standard sciences, chemistry, physics, engineering, biology of 100 years ago, those were the subjects. Really the boundaries have broadened, and now one could say that condensed matter physics, synthetic chemistry, molecular biology, materials engineering are now almost one subject, in the sense that you can say modern materials will require an understanding of almost all these subjects. And that means that we need to rethink our education, and certainly when it comes to research in materials, you will need a cross-disciplinary approach and have people who have an understanding of condensed matter physics. You'll need people who really are chemists, who really understand the interaction of atoms, hydrogen interactions, weak interactions, van der Waals forces, who understand the electronic properties of molecules, spectroscopy, because that's going to be interesting and important for molecular electronics. Molecular biology, assembly, bottom-up assembly. And for instance, the brain is a very complex, maybe a computer-type object, but it's been built by bottom-up assembly. Engineering, materials engineers, are really people who need to make it happen, the technology, and to assemble these devices into useful sort of major computers and stuff like that. So modern science is incredibly exciting but very broad, and I think we need to recognize that. I think we still have to be specialists in one or other area because it's such a hard thing to do, but we need to work together with people, and really they have to trust the expertise of other people. And I think this is a problem because the universities are rather locked into these traditional departments. I mean, physically in the buildings. I mean, there are materials science and engineering, but now the new term nanotechnology. I like to call it nanoscience and nanotechnology, N and N, because the nanoscience is the fundamental part of it, the nanotechnology is the applications of it. And I like to marry these two together because that's the way it is. But it's not really new. I mean, there are many different definitions. One could be atom by atom, molecule by molecule assembly of a complex system. And that's what we're trying to do. I mean, if we think about the modern technology of the computer, it's top down. We create a piece of silicon and we make it, and then we cut it up into smaller and smaller pieces. The question is, can you make a computer by bottom-up assembly? Well, this has been created by protein assembly on the basis of a DNA blueprint, so we know it can be done. The challenge is, can we do this? Well, maybe one day we shall. It's a long way off. And if you recognize this, then you say, okay, we need to learn something from biology about assembly of complex systems. We need to learn something from about biology in the way that our body, all these test tubes of chemicals work together. To understand what's in the test tube, we need the chemistry. To understand the interactions on a very small scale, when we're talking about molecules, we need to have a chemist's understanding of the interaction, and then we need the physicist's understanding of the intricate details of the condensed matter behavior. So it's a very exciting time, but one very challenging, because one person, I think, cannot know everything. And so we work now in teams, and we must bring all those teams together really under one roof. I think if they're still separated in the 20 years' time into chemistry, physics and biology and engineering, I think we're going to have problems.
Okay.